Welcome friends to my YouTube channel Sommo Physics. Today I have to discuss about the gravitational potential and its simple application. So what is gravitational potential? That I told that amount of work done in taking an object from infinity to any point in the gravitational field is called the gravitational potential. Okay. Work done in taking an object from infinity to any point in the gravitational field. Any point in the gravitational field is called gravitational potential. Gravitational potential at that point. Okay, this is simply the definition of gravitational potential. Work done in taking an object from infinity to any point in the gravitational field is called gravitational potential at that point. Okay, so we will take one example today, which is simply a spherical shell. At first we consider the spherical shell. Okay, now suppose this is the spherical shell. Suppose this is the spherical shell of radius A. Say this is radius A. This is the center and we take a point P. Okay. Now we all know that this spherical shell is composed of large number of slices. Okay. Large number of slices can form this type of spherical shell. So we take such a slice, say this and this. Okay, so we join it. So the slice is say A, B, C, D. Okay, now what will be the distance of the point P from the slice? This is simply that, and we call it X, say, and this is say R. That is the distance between the center and the point P is R, and the distance of the point P from the slice is X. Okay, so simply if this is theta and you take this is small angle d theta. Okay, now since d theta is small, this is also A. So what will be the width of the slice? Width of the slice will be this AB, that means A into d theta. And what will be the radius of the slice? Simply this line, which is nothing but A sin theta. And radius of the slice, this is simply A sin theta. Now if rho is the mass per unit area of the shell, okay, mass per unit area of the shell, then what will be the mass of the slice? What will be the mass of the slice? This is simply circumference into thickness. Circumference 2 pi into radius, which is A sin theta. And what will be the thickness? A d theta. So this is simply A d theta. So this is the mass of the slice, and if rho is the mass per unit area, then this is the total mass of the slice. Circumference into thickness. Circumference 2 pi r. R means A sin theta, and thickness is A d theta. This is the area, and mass per unit area is rho. So this is the mass of the slice. So 2 pi A square rho sin theta d theta. Okay. Now this is the mass of the slice. Now we all know the formula of gravitational potential. Okay, we all know the formula of gravitational potential. What is it? Minus gm by r. So what will be the potential at P due to the slice, this slice? if the potential is dV, then this is minus G into M. M means 2 pi a square rho sine theta d theta by the distance. And what would be the distance? That is x, the distance of the slice from the point B. So this is the formula. Now if you look into the picture, then this forms a triangle, okay? And since A and R, these are opposite vectors, the resultant can be written in this way. That is a square plus r square plus 2ar cos 180 degree minus theta. This is equal to x square, okay? Since A and R are opposite, we can write from the triangle law this, okay? So what we get? We get a square plus r square minus 2ar cos theta. This is equal to x square. So if we differentiate it, then what we get? This is simply 2ar sine theta d theta, because these terms are constants. These are constants. This equals to 2x dx. Now what will be my sine theta d theta? This is simply my sine theta d theta will be simply 2x dx by 2ar, 2x dx by 2ar. So that means x into dx by ar, okay? X into dx by ar. So this is the simply sine theta d theta. Now if we substitute this value in that equation, so what we get? If we substitute this value in this equation, so what we get? We get simply dv, this equals to minus g into 2 pi a. We write dv, this simply minus g into twice pi a. The pen is not, marker is not working, so I write here so x dx by ar. So what will be my dv? My dv will be minus g into 2 pi a square rho into x into dx upon r by ar, okay? And this is also x, so this cancels. So what we get? Minus g into 2 pi a rho dx. So this is the general formula. Now this formula can be varies depending upon the position of p. Now there are three cases. If in that particular case, if p lies outside, then what would be the potential due to the entire shell at p? This is simply, if p lies outside, then r is always greater than a. So the limit of integration will be r minus a to r plus a. This is simply minus twice pi a rho g dx, okay? This is simply this. So if we simplify it, minus 2 pi a rho g, it would become r plus a r, it would become r plus a minus r plus a, okay? Minus r plus a. So what would be the result? The result will be minus 2 pi a rho g into 2a, okay? This is the result. And oh sorry, there will be a r in the, there will be a r term missing, okay? So simply there is a r term, sorry for the mistake. So the result will be 4 pi a square rho g upon r. Now what is 4 pi a square? The area of the slice, and rho mass per unit area. So this term represents the total mass, so which is capital M. So there we can see that for a point lies outside the shell, the potential is nothing but minus gm by r. Okay, the potential is nothing but minus gm by r. Okay, now what would happen if the point lies inside the shell? What will be the expression? Okay, what will be the expression if the point P lies inside? Okay, so let's check. Now we all know if the point P lies inside, then this condition occurs, a greater than r. So if we integrate this expression, that is minus twice pi a rho g upon r within the limits a minus r to a plus r, then we will find the potential at P when P lies inside the shell. So let's do it. So what will be my result? Minus twice pi a rho g by r. This is simply becomes 2r. Okay, so r cancels. So minus 4 pi a rho g. So if we multiply it by a, so what we get? By a. So this is simply minus gm by a. Okay, so this is simply minus gm by a. So we have seen that according to the position of the point P, the potential varies. Okay, the potential varies according to the position of the point P. Okay, and what are their expressions? That we also derive in case of a shell. Now P, if the point P is outside, then we see that the potential is minus gm by r. But if the point P is inside, we can write V is minus gm by a, where capital M is the mass of the shell. Now what happens if the point lies at the surface? Simply this is r equal to a. So at surface, what we can write? At surface we can write V, put r equals to a, so minus gm by a. So no matter whether the point P lies inside or the surface, the value will be same. So we see that the potential at the point P when it lies inside the shell and on the surface will be same, and this is equal to minus gm by a. So this is the simple calculation of a spherical shell. Okay, this is the simple calculation. Now let us move to another problem. In what happened in case of a solid sphere? Okay, what happened in case of a solid sphere? Because a solid sphere is made up of large number of spherical shells. Okay, large number of spherical shells. So at first we do the calculation for a point outside the sphere. So let us calculate this. So a sphere is made up of large number of spherical shells. Say this is one, say this is one. So sphere is made up of large number of spherical shells. Say this is of mass m1, this is of mass m2, this is of mass m3. And if you take a point P at a distance r from the center, then it is very easy to find out the potential at a point P outside the sphere. We all know that what would be the potential at P? The sum of the potentials of different shells, that is V1 plus V2 plus V3 plus dot dot dot. That means we can write minus G into M1 by R minus G into M2 by R minus G into M3 by R dot dot dot. So what we can write? Minus G upon R we can write m1 plus m2 plus m3. So this is simply capital Gm by r, where m is the mass of the entire sphere. M is the mass of the entire sphere. M is the mass of the entire sphere. Okay. So in our today's lecture, I shall discuss about the gravitational potential and take the example of simple spherical shell, and we also calculate the potential at a point outside a sphere, solid sphere. Now in our next class, I shall do the calculation of potential for a solid sphere inside a point P, that we do in our next class. But today, now I have to discuss another issue that I have to discuss. Now a boy of class 9 told me to solve few mathematical problems. He gave me two mathematical problems to solve. So let's do that for that boy. Okay, so this is this is simply mathematics that the boy gave me two problems. Okay, so okay, his first problem is, it is from algebra, that if a plus 1 by a, this is equal to 1, then what would be the value of a cube? This is his first question. So just do it. Given that a plus 1 by a, this is equal to 1. So what we get? A square plus 1 upon a, this is equal to 1. And from which we can write a square minus a plus 1 equal to 0. Now we can write a cube as a cube plus 1 minus 1, right? So what we can write, a cube plus 1, that is simply a plus 1 into a square minus a plus 1. So what is this? This term is 0. So 0 minus 1. So this is minus 1. So this is the result. At first you simplify and then you can write a cube as a cube plus 1 minus 1, and the formula of a cube plus b cube, we all know, factorized formula is a plus b into a square minus ab plus b square. So substitute that value, then you will find it minus 1. So this is the first problem. Now his second problem is that given that the diagonal of a sphere is given x minus 5 centimeter. Okay, his second problem is that given that diagonal of a square is given x minus 5 centimeter. So what will be the area of the square? Find out the area. Okay, now we all know that the diagonal can be written as root 2 into length of the arm, say L. This is given x minus 5. So what will be my L? My L will be x minus 5 by root 2 centimeter. So what is the area of the square? Area of square will be L square simply. So what is the result? X minus 5 whole square by 2 centimeter square. Okay, so this is the answer. So the formula of the diagonal of a square is root 2 into length of the side. This is given x minus 5. So L will be my x minus 5 by root 2. So the area will be L square, that is x minus 5 whole square by 2. So these are the two problems that a boy of class 9 gave me few days ago, and this is the result. Okay. So dear guys, if you don't subscribe my channel, then kindly subscribe it and share it to your friends to get latest updated videos on higher secondary physics and also graduation physics. Okay, thank you.